chapter 1 in signal and system. We're going to learn about signals first, and then we're talking about sampling, then systems, then periodic signals, discrete time sinusoid, real exponential, complex exponential, unit impulse, and manipulation of signals. Now, I have removed the MATLAB exercise from this slide. They are all available on the lecture notes, so you can look at the lecture notes. Otherwise, it will be too many slides for you there. And also, I think I have removed the problem sheet, which is also available on your lecture notes. Okay, let's start chapter 1. What is signal and what is the system? That's what we're going to learn. So basic things that you have already learned in year 2, in the second year. Okay. So the term signals and systems have got various interpretations. Signals could be an analog signal or digital signal. Analog signal is continuous in time. We call it continuous time signal. Discrete signal is values you have got at discrete time intervals. So, for example, signals are voltages or currents, and they are related. Voltage and current are related by an equation when they pass through a system. So here is a system, for example. That is a system, and input is a signal, could be a sinusoidal signal, and this is an output voltage, that could be a signal as well. The system consists of a resistor and a capacitor. In this case, this system is a low-pass filter. This is a low-pass filter, and I'm sure you have done last year. If you work out if you look at the frequency response of the low-pass filter frequency against amplitude, it looks like this, a low-pass filter. And the cutoff frequency, 3 dB cutoff frequency, will be somewhere here, where this will be F equal to 1 over RC. That's your cutoff frequency. This is, if you take this is at 1, and this will be at 1 over root 2. I'm sure you've come across this before. So just to show you a simple system with a signal input and output. Normally the block diagram is shown as, here is the system. This consists of a resistor and a capacitor in this case, the previous example, and the output here, the voltage equals the capacitance to the output, and input is here, input voltage to the system. So that's the basic system that I've shown you there. There are 2 types of signals available. One is continuous time signal, other is discrete time signal. In the case of continuous time signal, xt is available to at any time instance. So t was xt by rho, and you can see if I have a signal like that, and I can find a value at any time instance. You name any time instance, there is a value. So that's the continuous signal. So t is the continuous time independent variable, which can have values between minus infinity and plus infinity. So this signal can go this direction as well. On the other hand, if you look at discrete time signal, that's what we need to know. So what is discrete time signal? They are only defined. They're defined only at discrete times. So for example, if I have a discrete signal, I could say I have got value there, value there, value there, value there. These are discrete values. These heights are correct. This is n, and the distance between these are normally equal. Our distance, that distance are equal. And we don't know what value is in between. We don't know what value is in between. But we know a value at that point and that point, not in between. So that type of signal representation is called discrete time signal. And this position, the position number 1 there, we call it n equal to 1, That is, we call n equal to 2 and so on. So this is an integer value. In a continuous time signal t, in a continuous time signal, this will be in millisecond or second, and here n equal to 0, 1, 2 and so on. So let's look at what is continuous time signal. For example, you take a body temperature of a person. The body temperature varies continuously. Every time instant there is a value. But when you measure it, you discretize the value. That means you don't measure continuously. You measure now, but later on, lunchtime, maybe in the evening. So you're taking discrete time instant values. So you're finding out the temperature now, and then later and later. You don't know what temperature is in between because you are not doing the measurement. So for an example, body temperature is a continuous value. The prices of stocks printed on the daily papers are discrete time values. Well, it's obvious because you know the stock at this time and then it will be tomorrow. You don't know in between. So this is discrete time value. Okay? Very simple. You've done this one. I don't need to go through this in detail. So here is a diagram showing you that here is the continuous signal, here is the discrete signal. So continuous signal is in t, it could be in second or millisecond. These are normally n, which can be 0, 1, 2, or it can be negative -1, -2 as well, this side as well. So what I've done is I've taken the continuous signal and I read the value at that point. I got that value. Then I read another value at that point. So I got that value. Then I read another value at that point. I got another value. And then I get another value here, and so on. So if you join these like that, roughly, you'll get this signal. So a continuous signal or analog signal can be translated into a digital signal. But important when you are doing this translation, you want to make sure you're looking at the value at that time instant, and next time when you look at it at that time instant, this distance, what we call is the period, and that time instant, they must be same. When you convert an analog signal into discrete signal, and they must be same. We'll come to the next slide. So that's what we call sampling. So if you go back here, converting from here to this signal, we use something called A to D converter, analog to digital converter, which does this job. So what we give you is xt is what's provided here. It's a continuous signal. What you get out of it is called xn. And let me come back to the symbols in a minute. And they are discrete signal at different time instance you get the values. How do you represent these signals? Let's look at it. Discrete time signal is what you're going to do. You need for digital signal processing, you need discrete time signal. So xn is your signal. xt is your analog signal. What you're doing is you're saying I'm looking at the analog signal at t equal to nt. That means every time instant, 1 sampling, 2 sampling, 3 sampling. That means it's here. Take a position, and I'm saying this is xt, t, that's xt, and I'm saying I'm looking at t equal to t. So I'm looking at that position. That I call it 1t. That's why here n equal to 1t. Second value, I'm looking at it there. That position is equal to 2t. And the third value I'm looking at here, that position is equal to 3t. Now what happened is because the t is common, we know t is the distance between these two, that's the t. We now ignore these t's, and now from now onwards, when you have a discrete signal, you will have only 1, 2, 3. And we just say xn, n goes from 1, 2, 3 and so on. You can have 0, can have -1 and everything. And how do you obtain the discrete signal? Take the analog signal and look at its value at t equal to nt positions. There. Is that clear? Okay, let's move on. Remember, when you are doing the analog signal, you normally say xt, or when you have a discrete signal, you will say x square bracket s. That's your symbol for discrete signal. Now, the process of sampling. We are learning sampling now. What is sampling? You take an analog signal, xt, and, for example, think as a switch. You close this switch at this rate. That means you close now after t seconds, then close after another t second, then close after another t second. So, when you close and open, this signal is now converted into discrete signal. That means we are looking at the analog signal at nt, every nt position. So, Fs, which is 1 over t, takes a special name. It's called sampling frequency. T is called sampling interval. We don't call it as, some people call period, but it's really sampling interval. Now, I'm sampling at that point and that point. The distance between that is called sampling interval. Once you have determined the sampling interval, you have it always constant. You don't change it, okay? Here is another example that you've already looked at it. Here is the analog signal. This analog signal, I haven't drawn it here. It will be continuous like that. That's the analog signal. And I've got t here. And I'm trying to find out where is the zero position. Okay, I'm reading a value. So exactly the same value what I have here. Then I'm moving my sampler at t position. This is my t. And I'm reading that value. So that's value. Now then I'm moving this, I'm switching and closing and looking at a value at 2t. So this becomes that value. And then I'm looking at the value at 3t. And then that becomes that value. Now, as I said to you, for discrete signals, you don't write this t all the time. We know the t is always there. So we just put it as 0, 1, 2, 3. And it's shown now the new discrete signal I'm going to get. What's going to give me xn is going to be, the values are, the first value is 3.5. My second value is 4. My third value is 3.25, and so on, so on. The first value occurs at n equal to -1. This is -1. Second value occurs n equal to 0, and n equal to 2 is here, and so on. That's how you represent a discrete signal. You can, instead of drawing a picture, you can represent it like that, a sequence. Sequence is a discrete signal. It's important to recognize that xn is only defined for integer values of n. So between values, between two values, this is n equal to 1, n equal to 2, you don't know what values, because the waveform could be like that, waveform could be like this, so we don't know. So in discrete signals, we do not define anything between integers. We just say it's not correct to think xn is being 0 for n not integer. That means you can't say at 1.5 the value is 0. That's not right. You can't think. You do not know the answer is. You do not know at all. So xn is simply undefined for non-integer values. We haven't defined it. If you really want to find out, you have to do some sort of interpolation. But we do not know the value, okay, at the moment. So discrete signal has only value at the discrete time instant, not in between. Think that very carefully. Now we come to sampling theorem. What is the sampling theorem? Okay, you have already done before possibly. You want to look at what frequency you're going to sample the analog signal. What's the purpose of converting an analog signal into a digital signal? Because you want to process the signal using a computer. So you can't process what is coming out of a person's mouth is an analog speech. If you want to process that, you have to convert into digital and use the digital computer to process it. Now, then you have to decide the sampling period. How do you decide the sampling period? In order to decide, so if I take a signal here like, that's a speech signal, speech. That's with one-to-one communication between two persons. The bandwidth of the speech, the bandwidth BW is roughly 0 to 7 kilohertz. That's what we get normally, the bandwidth over one-to-one speech. If you say telephone speech, the bandwidth is 0 to 4 kilohertz. So what they do is they remove the remaining 4 to 7 kilohertz, because smaller the bandwidth is better, you can compact a lot of stuff, okay? We'll come back to that later on. If you take music, the bandwidth is 0 to 22 kilohertz. So the problem is, at the moment, because of various bandwidth of signal, that's just 3 signals. There are other signals, ECG, electrocardiograph signals, low bandwidth signals. There are many other signals available. So I'm just taking this signal, and then you need to first know what is the maximum frequency here. 7, in this case 4, in this case 22. Based on that maximum frequency, you decide the sampling frequency. So if I'm going to sample what's coming out of the mouth, then my maximum is 7. So the sampling theorem says, then you must sample Fs greater than or equal to twice the maximum. So you can now turn around, if a speech, my sampling must be here, Fs must be greater than or equal to 40 kilohertz. What about telephone bandwidth? Fs must be here, greater than or equal to 8 kilohertz. What about music? Because 22. So the sampling has to be greater than or equal to, yes? What do you think? 22 multiplied by 2, 44. So Fs should be greater than or equal to 44 kilohertz. So your normal CD, when you listen to digital music, it's at 44 kilohertz sampling rate. It's 44.01, or sorry, 44.1 actually, kilohertz. Okay. So you can see that's how you select your sampling frequency. That means, what does that mean is, here is your music signal. You want to find out at what rate I want to sample. What's the distance between that? That distance is the sampling period. So we say that distance depends on your maximum frequency content that you have. So hope you have understood that. We move on to the next example. Let's take an example I have already explained to you. The audio CD uses a sampling rate of 44.1 kilohertz for storage. The sampling frequency is slightly more than the maximum frequency available. Maximum is about 20. Well, it's really 22. Not really exactly correct to say 20. 22. Because the ear bandwidth is about 22. So that's how because if the ear bandwidth is 22, then your sampling is going to be more than 22, double the time. That will be 44 kilohertz. Okay? So 22 kilohertz is generally the accepted upper limit of human hearing and perception of music sounds. Okay? So before you do convert an analog signal into digital signal, you must first find out what's the maximum frequency the analog signal has. Once you know that, then say twice that is what you have to do, minimum. You can have more than that, but twice with that, you should have no problem at all. If you don't go for it, what happens? Then you cause aliasing, a distortion in your signal. If you do not sample at 44 kilohertz, in this case in the audio, you will cause distortion. You will able to, when you play the signal back, you will able to hear it. Okay? So that's theory. We will come back to that later. This is just basic introduction at the moment. So here is an example. I have got a signal here. My bandwidth of the signal is 40 hertz to 5 hertz, 5 kilohertz. So what is the minimum sampling frequency you need? So you go and say locate, that's my maximum frequency available. So minimum sampling frequency, my Fs must be greater than or equal to twice the S maximum, which is twice times 5, which is greater than or equal to 10 kilohertz is your sampling frequency. Or 20, 30 you can use, but must be minimum 10. That's how you do the calculation. Now let's come on to some signals. We are going to look at different types of signals. In order to analyze the system, you must have a certain input. So we have certain defined input. First one is called unit step input. We have done it last year. Unit step input is basically tells you, here is my signal. At t equals, this is t, this is analog, yeah? This is analog, you can see that? And this is 1. When t is less than 0, this part is all zeros. When t is greater than 1, it's greater than 0, it's 1. So that's your signal called step. Step means 0 and that means give you a step, right? And the same thing, if you convert them into discrete, so ut, if you sample at n equal to t, you get un. So if you do the un, which is your discrete step, which is 1, now this becomes n is greater than 0, n is less than 0. So ut, when you're writing a ut, the same thing is 1 when t is greater than or equal to 0, 0 when t is less than 0, but un is the discrete version of that. That means defined as only discrete values. So let's go for and look at that. Here is your difference. This is your t equal to 0. This is ut, and it's 1 you can see. And this is un. Un is defined that point, sub point, sub point. You can see that, at definite point. In between we don't know. So it's 0, 1, 2, 3 are the positions. That's the difference between ut and this is un. So I'm just defining signals. All these are later on required, okay? So it's just, those who have already done this might find it boring, but just, you can skip it, you can move forward fast, right? Here is another signal I have. I have defined, I want to sketch this waveform. I have un, which is here. This is my un, discrete value. And I have un minus 1. Un minus 1 means you shift to your right by one sample. This means one sample. One sample. So you take your signal, this signal, now move everything by this way. So you move there, this one move here, this one move here. So that point move here. So you can see this waveform now has moved from 0 to 1. That's where it starts. This line is at 1 position. You see here? It's in there now. At 0, it's nothing here. 0 there. Earlier at 0, you could height. So the waveform is shifted now. Now if you take this waveform and this waveform, these two, and if you subtract, that's what it says, subtract. When you subtract, what will happen is, that's gone, because 1 minus 1 is 0, 1 minus 1 is 0, and so on. What happened to this one? This is 1 minus 0. It's 1. And these are 0 minus 0, they're all gone. So what's left is 0, 0, and a big 1, and a 0, 0, 0. So this sequence manipulation is to get another waveform from a standard waveform. This is a standard waveform. From that, you get a new waveform. What is this called? This has got a special name. This is called impulse. Impulse means it has got only one value at delta equals 0 and is 0 everywhere else. That impulse can be at delta equals at n equals 0, n equals 1, it doesn't matter, but it only have one value of unit amplitude. If you have unit amplitude, it's called unit impulse. That means if this value is 1. If this value is 5, then you just call it impulse. Okay? Here's another example. This is an analog waveform. I take un. I know what is like that. T plus 1. T plus 1. So you move to your left-hand side. So you move your waveform to the left. So it should have been at 0. Now it comes to minus 1. Because you have to move by one position. And then this is 2ut. That means take ut, that's 1, multiply by 2. So that becomes 2 here, 2 ut. So you got a waveform now, 2 ut. And then you've got ut minus 1. That means you take the waveform, shift this one to this side. So when you do that, it moves here now, that point. It's going from 0 to 1 because you shifted there. Now what happens is you subtract this one minus that one and plus add this one. So go sample by sample, that, and write the equation. Eventually when you do the subtraction, you get that waveform. And if you're not sure about it, you can ask us in the tutorial class. All you do, take a value. If you want to take a value, take at that position, at 2, right, at 2 position. Take this example. You want to, okay, let me rub this out for a second. So you get a full idea of what we are trying to do. Let me rub this out. So you understood how to do the shifting. Now let's rub it out. And go through a one value iteration and see how it works. So let me take a value at what? 2? Right. Okay, I want to take a value 2. So I want to know y2. What is y2 is equal to? You are saying y2 is equal to, you're going to put 2. u3, yeah, minus 2u2 plus u, because 2 is here, u2 minus 1. So what is u3? u3 is, here, in this waveform, u3 is 1. So it's equal to 1. Minus twice. What is u2? u2 is here. u2 is 2. So, 2 times of u2 is 1 there. So, plus ut minus 1. So we'll go to this waveform, and 2 minus 1 is u1. u1 is 1. So what's the value at that point? So we are evaluating at this point, yeah? So what's the value? This will be, that's 2, that's 1, 1 minus, that's 2 minus 2 is 0. This is equal to 0. So you must see at 2, it will be 0. Yes, it is 0. Have you seen that? So that's how you evaluate. So just substituting the values, you can, okay? Remember here, don't make a mistake here. This is ut, u2 is always 1, yeah? And twice of that. Or you look at the total thing from here, which is 2 there, with 2 combined. Okay? Now we come to a system. So far I talked, what did I have talked about? I've talked about signals and discrete signals, continuous signals, and then I looked at sampling, and now we come to a system. Here is a continuous system, right? So I give a continuous signal to the system. I have a continuous output. That's analog system, right? So general representation of a continuous signal. Let's move on to the next one. Discrete system. I must give them discrete signal I have to give. When I give discrete signal to a discrete system, I get a discrete output. Now the question is, how do you define a discrete system? How do you define a continuous time system? Okay, let's look at that. You will learn, or you have learned before, that continuous time system can be represented by differential equations, whereas a discrete time system can be represented by difference equations. See, this is differential, this is difference equation. We learn that in a minute. So because everything is based on difference equation for a discrete system, and continuous system is a differential equation. You have done that in the second year. We won't be doing that, but I'll show you one demonstration. I want you to think, one thing you have to do is remember, if you have xt, it's your analog system or continuous time system. If you want to go to a discrete time system, you replace t by nt. Remember, we looked at before? You sample at every time instant, right? T time instant, t, 2t, 3t, 4t, that's your sampling. That's how you go for analog system to a discrete system. sampling from analog to discrete. That's just equation you use. Okay? Now, what we are going to do here is now, we're going to look at the system, and by looking at it, you know yourself, this is an analog system because ET, input is a continuous input, output is a continuous output, and this is an analog system. Now, we want to represent the system, and this is the system. This between that point, this is the system. And how do you represent this system? You have done last year, or year 1, to write an equation for this. For an analog system, you can write a differential equation. The voltage equals this capacitor, differential voltage equals capacitor, plus the VC is equal to 1 over RC ET input. We know how to derive this, and if you are not sure how to derive this, just ask us in the tutorial class. We can show you how to derive this. Very basic equation of deriving the voltage equals this circuit. So you apply Kirchhoff's law, you say ET is equal to supply voltage is equal to IT times R, that's the voltage equal to this, plus VC. And then you start substitute for I, and then you can get this one. Okay? This is now, because it's an analog system, this equation is a differential equation. You see? It's not a difference equation, it's a differential equation. Differential equation will have a first derivative, second derivative, third derivative, and so on. Right? Normally, first and second is what you will use. And now I've determined I want to convert this differential equation into difference equation because I want a discrete system. The low pass filter that you had, this is a low pass filter. It's a low pass filter. I want this low pass filter is represented by discrete system. This low pass filter is given by a differential equation, but I want to convert that into a difference equation to make it a discrete system. How do you convert that? You look at that part. That's the differentiation. What's the differentiation? Is finding a gradient. So if you've got a waveform here, if you want to find the differentiation at that point, you take very two close points and find out this value y1, and this value then y1, this one is delta. And you would say this is like, say if you put x, the gradient or the slope or gradient is, you will say y1 plus delta minus y1, that height, this height. It's on the next slide, but anyway, that height, divided by that one, so tan. So divided by this length, okay, delta x. So it's delta x. It's on the next slide, okay? So all you do is to take two values next to each other and divide by the distance. If you look at our, just drop this out for a second. If you look at our discrete system, just take a discrete system. Remember? Like I'm going to draw a discrete system there. So I got a value here, 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 I got a value here. I could say that value and that value, that position I could say is this one, this position, I could say is nt, like any t, like, you know, n times of t. T is the sampling period. This is the value before. So I could say that will be nt minus t, because just one sampling, this is t. So I can say, what's the output here? That output is, this output is DC, capacitor output at nt position, that height, minus this one is that position, nt minus t, that value. Both of them, that's the difference. So that will give you this difference. That divided by t is that distance, is your slope, is your gradient. So the differentiation, this is a gradient, can be calculated by finding on the discrete output there and there, subtract them, and then divide by the distance. Now, if you do that, your equation now, you can replace this one by that. And go to the next slide. I've shown the same diagram the next slide. Here it is. DC is the capacitor output, and that point is given, You have the value and you subtract them. This is called backward Euler approximation. You've probably done this last year. You have to. This is only true if the t is small enough. If t is very big, then the differentiation does not work. How do you work it? Like, because if you have rod and you put one here and one here, you're going to find the slope like that. That's not right. So this only works. This approximation only works if you're taking points very close to each other. So I'm only trying to show this is not the way we'll be always doing it, but this is a good approximation. So now I'm going to replace my differential equation, the differentiation, by this. Okay? Let's move on. Differentiation has been now replaced by that. And you have got BCT earlier. When you go for discrete, it will come as BCNT. Remember? Whereas T has to be replaced by NT. So that's BCNT. Similarly, ET is ENT. Normally, when you do differential equation, we know T is the sampling period. So we don't normally leave T here. This NT means N. NT means N. This T is normally taken out. Like, we drop out. We don't drop out here. This is the division. But here, we always say, right, let's take out the T, and we don't write as X in T. We write as X L. Right? So from now onwards, now don't forget, now I've converted all these square brackets into round brackets. It should be square brackets. I mean, that's not correct. You can't have round brackets, but it should be square brackets. But what happened is that when you're writing it, in an exam, there's nothing wrong if you use round brackets, because the square bracket takes a long time to draw. So you can use round brackets, but strictly in books you will find square brackets. Now, if I remove the NT, this will become BCN, this will become BCN minus 1, remember? And T will be still there for that. Then this will become BCN, this will become EN. Now I've got an equation. If we just move this up in both directions and trying to find out the value of BC, BCN equal to BCN minus 1 plus EN. So what does this equation tells me? I can find the value across the capacitor at this time instant, that's the current output, is equal to some constant time my previous output. BCN minus 1 is my previous output, previous capacitor output, plus the input, multiplied by a constant. So what I do is, in this circuit, take my input, multiply by a constant, have that ready, and take my previous capacitor output, multiply by a constant, add them together, I get the current capacitor output. So that's how you work the discrete system. Discrete system now comes as this. So I have shown you how to convert a simple differential equation into a discrete time system, which is a simple difference equation here. Okay? By using a small approximation technique. It's important for you to know this technique. You must know this one. So, from now onwards, continuous time system and analog system, and continuous time, so analog input, continuous time system is represented by differential equation, and output is analog. If it's a digital system, you will have a difference equation. Okay? So you can simply say, for a low-pass filter, or for a low-pass filter, the equation becomes as BCN equal to like a constant K1 times BCN minus 1 plus a constant K2 times EN. That's what we proved earlier. That if you implement that filter, that becomes as a low-pass filter. Like, how do you find the cutoff frequency of a low-pass filter? Well, we will learn that later. You have probably done it. This is your cutoff frequency. It's called 3 dB. This is 0 dB. There's minus 3 dB cutoff frequency, and that's the cutoff frequency that's 3. We will learn that how to calculate that later. So this is a discrete system, and this is called a difference equation. It's a difference equation. Okay? Right. Let's finish this up for a second. The advantage of this sort of lectures is that you can actually skip some part if you knew already. Just skip them. Just move the bar and you can just skip them. And this sort of lectures, I think, is much better than being in a class and trying to concentrate and then you're trying to write things. I'm writing everything. You can write a notes based on what I'm saying, or you can revisit the lectures. Okay? Give me your feedback later on after you have watched the lecture and see how it goes. Okay, let's go example. Few examples. I have an analog signal which is called xt equal to e to the at, and t is the time. And I want a discrete analog signal. How do I get that? Sorry, it's not a discrete analog signal, beg your pardon. It's a discrete time signal. How do I get that? I substitute t is replaced by nt. N is the integer and t is the sampling period. So xn, you don't change it here. Remember I told you? Here in the equation, t is replaced by nt, so you get e to the ent. And t is the period, so fs is sampling period. So, and these are sample numbers, like this. This is not right, this is not, make a correction please. This is not right, this should be there. See that? In your notes, if it's there, it's not right. It should be like there. N is 0, 1, 2, 3, and period is that. Take another equation, xt equal to that. How do you convert into discrete equation? You replace wherever t, in this side you replace t by n. Here t is nt. So wherever t you put nt, and your equation becomes sample number. Sample number is that one. That's the sample number, right? And 10 e to the minus nt is that one. But you must know for discrete system what's the sampling period, and you should know. Otherwise you can't really work out. Now we have got another system where we got an analog cosine waveform where omega equal to 2 pi f a. This is important. You need to concentrate this. You need to rewrite this yourself and see whether you understand. Okay. Xn equal, if you do discrete, you will get that. How do we get that? Let's start. Let's start from here and say t should be replaced by nt. Okay, so I do that, a cos, and omega a, I'm going to substitute that. So it's 2 pi f a, and t is n t. Instead of t, I can say 1 over fs. Or I can say fs is equal to 1 over t. That's all same. So I put 1 over fs. I now group these two together. That one. And I get 2 pi fa over fs times n. We will now define this as theta, is a new frequency. This theta is called digital frequency. Just a ratio. This is analog frequency, this is sampling frequency. It's equal to a cos n theta. From now onwards, an analog signal xt is equal to a cos omega at. Then the corresponding digital would be going to be xn a cos theta n. That's where it will come. What's theta? You say theta is equal to 2 pi, the analog frequency, divided by sampling frequency. So the maximum value it can have is 2 pi, you know. So from now onwards, you've got something called digital frequency. Here's an exercise where you have been given a modulated signal. You need to find out what's xn. Go ahead and do the substitution and try them out. If you can't do it, ask us in the tutorial class. So you have reached a state where what is digital frequency? Somebody said, ask, what is this digital frequency? The definition of digital frequency is 2 pi fa over fs. Fa is the analog frequency, fs is the sampling frequency. Okay. And we will show later theta has got a range between pi and minus pi. Or you can write theta is greater than or equal to 0 or less than 2pi. You can do that as well. But this range is important, and we will come back to that later. So let's look at periodic signals. That's the next section that you have to look at. Basically, you have learned what periodic signal means. A signal at periodic means it repeats after certain time interval. Same value comes again and again and again at a regular interval. So we could say periodic means xt will appear again after p time p value. P is called the period. So that means, so if you take a sinusoidal signal like that, I could say that value appears here. So that distance is called the period. So you can write them as an equation xt is equal to xt plus p. Okay? So that's analog period. In other words, well, here it says the periodic signal has properties that is unchanged in time shift of p. So if you take the signal and shift them by p, you'll have the same value. Here's the waveform just showing you. Here's the signal. You can see this signal is repeating. This one is repeating at every p, like, it's repeating. So it's a periodic signal by looking at it. Same property applies for discrete signals, but you have to be a bit clever there. Just to understand, you have to be careful there. Not clever, careful, because xn comes back again after n samples. This is in terms of samples, because here look, if you take the signal, and this is a discrete signal, these are the values. I could say this signal I've got 1, 2, 3, 4, 5, 6 samples, 7, 8. I could say this value and this value is roughly same. So every 8 samples are same. So here is sample number. After how many samples the same value appear? Regular interval. That's called periodic in a discrete time domain. Let's look at one example. Here is an example here. You can see what's the period here. Yes? Now one are together. And the same thing repeats again. See? And the same thing repeats again. So what's the period? You could say 1, 2, 3. Every 3 samples, 1, 2, 3. Every 3 samples, it starts again. After every 3 samples, it starts again. So we can say the period is 3 samples. So you count how many samples, after how many samples it starts again. So it's 3, n equals 3. Discrete sinusoidal signal, I have already done this for you earlier slides. You can just run through them again. xt equal to a sine omega at, which is a sine 2 pi fat. Now I'm going to replace t by nt. So this will become xn, a sine 2 pi fa, nt, I have got n, t is replaced by 1 over fs. Now I can say this is called, this part is called the theta, so a sine n theta. And fs is 1 over period, and theta is that. So you can plot, if you want to plot a sine waveform, digital sine waveform, all you need to do, if you want to plot a digital sine waveform, you first calculate theta, which is equal to 2 pi, your analog frequency, you have to say, over digital frequency. And then you write a program to calculate A is equal to, not A, x n value is equal to, xn is equal to A sine theta, this theta here, theta, times n. You say n equals 0, you calculate that. N equal to 1, you calculate this. N equal to 2, so you can value x0, x1, x2, x3, and so on. You get fine. Now you have to be careful when you are doing this. there's a relationship between this. If FA is maximum value is 2 kilohertz, then this should be 4 kilohertz. Don't forget that. Sampling theorem. Sampling theorem tells you if your maximum frequency is 2, then this should be minimum 4 kilohertz. So you should write MATLAB code. In the notes there's a MATLAB code to plot the sine waveform and have a look at that. Now, what is periodicity? Yes, this is what period means. The same signal repeats after n samples. If I already know that xn is equal to a sine, I have already proved that, sine n theta. Now I can substitute this one here. Instead of n, I put n plus n, and this one here. Now you can say these two are equal, mean, what does that mean? Those two are equal mean that n theta, this part, is equal to 2 pi k. K is a number. So you can say I can find out the period n by dividing 2 pi k over theta, which is 2 pi k over 2 pi fa over fs. So this is how you calculate the period value, the periodicity, at how many samples is period. So in a discrete sine waveform, if you want to calculate the period, this is how you do. So you can set k equal to 1, and then you can just do the calculation. You can have k equal to 2, then it will be double the period, it will come, and so on, right? So you just say k equal to 1, and then n equal to 2 pi over theta. Here's an example. You have been told your analog frequency is 1000 hertz. So sampling has to be at least twice. That's 2000 hertz. But here is 8000, so that's fine. Fs has to be greater than or equal to 2 times of Fa, which is 2000 hertz is the minimum value. Maximum is 8000, that's fine. So if you are asked to find what's the how many samples, at every how many samples it will repeat, you can do this way as well. You can go back here, n equals to Fs over Fa times k from the previous equation, and k you can set to 1. So you take the sampling frequency, divide by the analog frequency, also give you n. So every 8 samples, the signal will repeat. Every 8 samples. So if you are asked to find out what's the period, if you have an analog signal, and if you sample at a particular interval, what would be the period in terms of number of samples? So the period n is equal to, you find out the sampling frequency divided by the analog frequency that you have, it will tell you what's the period. So take the next part. Here is an example. In this case, I have got, in this case, period n is equal to 12. So you can have 2 pi n over 12. You can see that as well. By looking at it also you can say, or using the formula also you can say. So you can see this waveform, roughly if you draw it, it looks like that. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Every 12, you don't count that because you already counted here. You have counted here, so you don't count that. So every 12 value is repeated. So you could write equation like that as well, right? Remember? So just to summarize, you can write xn you can write xn is equal to sine theta n sine 2 pi fa over fs n. You can do that, okay? Or you can move this down, upside down, and say equal to sine. This one is, you can write as 2 pi over fs divided by fa times n. This part, that part, give you your period in number of samples. That's equal to capital X. This is equal to K period. So just go through these examples again to work out. So you will be given analog frequency, digital frequency, and ask you to find out the period. That's the way you do it. It's very simple. It's not. Here is an example. You've been told determine the fundamental period of this equation. This is only amplitude, doesn't come into play. This is only phase. Phase shifting means this is only phase. Phase means instead of starting a waveform like that in 0, you start slightly later, or you start slightly early. So that shift is called the phase shift. That doesn't affect. So this value, by reading that value, you can simply say, what's the period? Well, I can just simply look at them and say 15. Or you can prove it. 2 pi times 1 over 2 pi over 15. Use this formula. We have done. So there's all sort of possibility you have got here. You can use this formula and k equal to 1. And you know theta is 2 pi over 5 because this is the theta. So you can say 2 pi over theta is in one way. The second way is, if you use this one, then n equal to 2 pi times 1 over theta is, this is theta. Theta equal to 2 pi over 15. And these two cancel, you get 15. Instead of that, if you can have it in that form, read out that value correctly. You can do that way. This is the best, correct way of doing it. So this question, you have been given, find the fundamental frequency. It's easy to do it. Here is another example. I have given you one more example here. Again, you have been told that fundamental period n is given for you and find theta. So you write theta is equal to 2 pi k over 1 and k is the smallest value, k is equal to 1. So theta is equal to is 2 pi over 10. So which is pi over 5 radians. So these are just for the sine waveform, how to calculate. Now we look at real exponential signal, this endless type signal. You have looked at already unit function, step function, so unit input and step function, or impulse and step function. Sorry, yeah, that's the best way, impulse and step function. Now we look at exponential function, which is in analog xt equal to e to the at. If you are asked to convert that into discrete, what would you do? You say t tends to nt. So it will become as xn, this should be square bracket, but anyway, c e to the power of a n t. That's your discrete signal. Okay. So I have to convert to discrete. So you will come across complex signals many times, so you need to know. So here is an example of a growing exponential. So this is xt is equal to e to the power of at. If you have a is greater than 0, this exponential will be increasing as t increases. If a is less than 0, then you see the exponential decreasing. So these are growing exponential and decaying exponential, which you have done many times. And if you have complex exponential, which you probably haven't done quite a bit, what you do, you write down this, and the amplitude is not real now. This is not real. So you just got complex value, c e to the jt. So you can write them as, in a rectangular form, c equals to that. And you can now say c equal to e to the at. C is complex, a is complex. So you substitute them. It becomes as c becomes that, a becomes this, and you manipulate that. Take the real parts together, take the complex part together, and you get, and then you expand this. This is e to the j theta is equal to cos theta plus j sin theta. You have done this complex exponential. So if you do that, this times that's there, this becomes cos omega naught theta plus omega naught plus theta plus j times, this one is still there, and sine omega naught t plus theta. So that's your complex exponential circuit. This has got real part as well as imaginary part. So you plot them. You plot them for various conditions. You go back here, again to the diagram. You say you're going to control this by this value, R. You make R less than 1 or R greater than 1. So if you do that, you can see here, because you've got cos already in there, it will try to do a cosine waveform like that. And then this is an exponential, which is going to do decay or it's going to increase one or the other. So when you multiply these, the cosine waveform will come under the exponential value. Just leave out this for a second, right? So you go on the diagram, you find when R is greater than, your cosine waveform was like that, constant amplitude. Because R is greater than, exponential is pushing it up, so your cosine waveform is just decreased here and it starts to increase its amplitude. When R is less than 0, you can see it starts a large value negative and then 0, and it will just decay. And this is important to know. For real signal, real-time signal, you will only go from t equals 0, this side only. You don't look at the negative part. So these exponentials are called damping or damped sinusoids, because this one is called damped sinusoid because it's decay. So damped sinusoid means it starts as like that and then decay like that. That's an example. Damped sinusoid is very useful. For example, an absorber, a damper in your car. When your car hits a ramp, there are dampers set up which will damp very quickly like that. Otherwise, the passengers will be pulled up. So if the damper is not good, it will go up like that and like that. The passenger in the car will be moving this way. Yeah, you would like to have that sort of car. So cars are set up with the dampers that when you hit a ramp, so it will just go up for a second, very less than kind of a 20 millisecond, and just come down quickly still. So you don't really feel this movement because it damps away the shock. So the dampers act like this. You will learn this in control systems when you go into the third year. Yeah, when you do next session control system course, you will learn about these dampers, how to design these. So if you take discrete sinusoid or times exponential signal, they will look like this, same as the analog but at discrete values. Or decaying, same thing but discrete. The equation is same. Xn, as I said to you, is equal to C alpha to the n. Alpha is any value. N is less than 1. Sorry, beg your pardon. Alpha, n goes always 0, 1, 2, 3 discrete. N goes from 0, 1. Whereas alpha could be greater than 1 or less than 1. If alpha is greater than 0 rather than 1, less than 0. If it's greater than 0, then you can see it moves our way. If it's less than 0, it's decays. Now, when you do discrete time system, you tend to start from for the real signal, you start from n equals 0. You don't go negative part unless you need to do it. For real signal is time n equals 0 and move forward. For mathematical manipulation, you need to have negative part, -1, -2, -3. Okay? So don't get confused between the analog and digital, just to get your ideas right when you're doing. Now, this is same thing. I've pre-plotted, I think. So now you go into the next one, which is another signal. So we have looked at step unit or unit step signal. We have looked at exponential signal. Now we are going to look at unit impulse. What is impulse? It's, as I said to you earlier, it's only one value which has got at one particular time instant. All other places, all zeros. If you look at the frequency content of this, so this is time axis. If you plot the frequency content, this frequency, impulse has got all the magnitude and all the frequencies at equal magnitude. You see, impulse. That's why we use impulse for testing a lot of things. It has got every frequency you name it. Impulse has got all the frequencies you name it, and they all would have equal magnitude. So if you want equal magnitude and all frequencies, you need to generate an impulse. So if you have got a system here, and if you want to check this system how good it is, you normally give an input as an impulse and observe the output. Because impulse would have every frequency, and then study the behavior of the system for all the frequencies. This is your system, right? So impulse is a very important function in discrete time system as well as a continuous time system, because it has got all the frequencies that come. And how do you basically this is just, if you integrate impulse, it will only give you 1. The reason why it does give you 1, because it only have one value. So if you integrate them from here to here, these are all zeros, and this is the 1, that's what you get. And you can actually take a step function, that's a step function. If you differentiate this, that would be 0. Differentiation there is 0. Differentiation here is 0. So if you differentiate at that point, you get a discontinuity, it's an impulse. So by taking a step function and differentiating it, you can get an impulse. Right? That's how you do in analog signals. Right? If you want an impulse. In discrete time signals, same equation, same thing. At only the discrete points it has got values. That's all zeros. At that point is 1. So it's called unit impulse. So delta n now, we don't call it delta t. That's why delta n equal to 1 and n equal to 0. There. And it's not equal to it's 0 and other places. That's called discrete time unit impulse. Unit means it's equal to 1. If this value is more than 1, you don't call unit. You say discrete time, sorry, you don't call unit, you call discrete time impulse. So if this value is 1, it's unit impulse. If it's not 1, say it's 5, then we call discrete time impulse. So you want to manipulate, simple manipulation of discrete time signal. How do we manipulate discrete time? A signal xn may be shifted in time. So you take a discrete signal, I'm going to shift to my right, it's called delay. And shift to my left is called advance. So if you shift them in time, it is n minus k is 1. So when k is greater than 0, it's called a delay. You just say n minus k. K is positive, it's a delay. If it's less than 0, it's an advance. So just take a signal. Here is the signal xt, xn. And if I move it to that direction by one sample, it will become xn minus 1. If I move it that direction by one sample, it will become xn plus 1. You can have 2 samples, you can have 3 samples, you can shift the signal, no problem. So that's the basic manipulation you need to know. Here is an example I have. Have a look at this example where this is my signal xn, right? I have shifted the signal by 2 samples, and I moved that position, minus 4 position, to here. Now that 0 appears here now. You can see here. So I have shifted to this way. In your case, looking at here, you're shifting to your right. So that means this is xn minus 2. And take the signal, shift them this direction now. That means this value comes here. So that's when you do that. Sorry, I'm only shifting by one value, not 2 here. The second example, so that's the first example is correct. In the second example, I'm only shifting this by one value. So that position will come here, this direction. So this will be xn plus 1. So you see, that one has come to that position now. So that is now here. So that's xn plus 1. That's how you do shifting the samples in discrete domains, shifting one direction, other direction. They all have meaning to it. We'll analyze them later. So you have your problem sheet A1, and you have to do all these questions you said there. You go through these signals. This is your tutorial number 1, and learn all these. And these are the other questions, tutorial questions. So you should be able to do all of these based on the lecture that I have done. And again, another question to find out the period. What's the period of the signal? So work out all these and try all these questions before you go to the tutorial class. Listen to the lecture, try all these questions, and then go to the lecture. That's your format. Go to the tutorial class. Let's look at a summary of what I have done. And this is the last couple of slides. What I've done, at the end of this chapter, you are expected to know this. What? Difference between signals and system. What's the signal, what's the system? You should know. Sampling theorem. What is sampling period? Sampling frequency. What is T? What is Fs? Aliasing. Aliasing, a terminology we haven't used it, which is distortion. That comes in the next section. The reason I put them in, you're going to look at it and say, oh, aliasing, what is it? We haven't learned. And you will go and look up a book. And that's my idea, that you want you to look at the book and see for aliasing. And I'll detail that aliasing principle in the next chapter. Right. How to distinguish between continuous and discrete time signals. If you are given two signals or equations, do you know whether continuous or discrete? How to distinguish between a differential equation and a difference equation. Where to use difference equation, where to. They are basic, but still you need to know. Then, what does the continuous and discrete periodic signal mean? Their definitions you need to know. Relationship between the analog and digital frequency. That's the relation. The analog frequency, sampling frequency, digital frequency. And theta is always less than or equal to pi and greater than or equal to minus pi. We'll come back to that later. And digital frequency. Manipulation of discrete time signals. You should be able to manipulate. And then you've got unit impulse and its properties. What's an impulse? Where you use them and its properties. Okay, that's to chapter 1. That's I have done for you part A, chapter 1. The CD will be available at the school office. You can collect them. We are planning to give CDs as we go along rather than one DVD, and we will record them. And if you want to give us any feedback, please give us so that we can use your feedback to record the next one. We can improve if you want us. Okay? Thanks very much. Okay then. Bye.
Thank you. Then